Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry. In our previous lecture we were discussing about pH and its applications in different situations and the different scenarios that we are observing today, like lake acidification, ocean acidification, and it is so important to address these challenges because it has immense impact on the entire planetic health. Today's lecture will be on redox reactions. Okay, so we have discussed some of the sources and now we are trying to discuss some of the processes that controls the concentration of different elements in the aquatic system apart from the sources. Okay, so sources is one thing, but then pH, redox, all the solubility complexes, adsorption, desorption reactions, these fall under processes that are dynamic and happening continuously in any aquatic system. Okay, so let's start with this redox theme today. Now, many elements, especially those elements which are in the transition group and in anion forms, they can exist in multiple oxidation states, okay, because that depends on the number of electrons they are exchanging, right. So, the complexes they are forming, in which form it is more soluble, in which form it is more mobile, okay. So, they can exist in different oxidation states. Okay. For example, here the different nitrogen, sulfur, iron, manganese, which are extremely common, okay, are very commonly found in all aquatic systems. Okay. They all are existing in different oxidation states. And why do they exist in different oxidation states? Because it depends on the oxygenation, the amount of oxygen available in that system. Okay. If there is a lot of organic matter decaying in that particular aquatic system, the system moves towards more reducing conditions. Okay. That means it will take any oxygen that is available, it will interact and again it will form decayed products, right. So, organic matter decay, then lack of oxygen exchange with the atmosphere and growth, excessive growth of algae, these all deplete the water of its oxygen concentration. Due to these continuous changes, so oxygen is not maintained at the same level continuously, right. It is not that it is continuously exchanging oxygen with the atmosphere at the same level throughout. So, there will be zones where the oxygen exchange will be very slow and less and can be impacted by different activities, mostly biotic activities such as organic matter decay, excessive growth of algal, phytoplanktons, cyanobacteria. So, all these kind of different biotic interactions continuously change the oxygen concentration in the water. And not only direct oxygen, any other species which can act as a oxygenation agent or a reducing agent. So, either oxidizing agent or a reducing agent, they can also alter the oxygenation state and cause alterations in the chemical composition. And certain species of these compounds, they are more soluble, they are more mobile, some are more uptaken and therefore they are bioavailable, some other forms are less toxic, they gets settle down in the sediments, they are insoluble. So, all these properties depend on the oxidation states. They control the further the complexation states. That again is related to the uptake, bioavailability, toxicity of all these elements. Not necessarily all elements are toxic, right? Only beyond a certain exposure level they are toxic, but not all elements in all their forms are also toxic. Certain species of the elements, certain species of the toxic elements are only toxic. Okay. So, we need to understand which state these elements are. Okay. So, for example, chromium, arsenic, all of these exist in multiple oxidation states, and only one of that state is toxic in nature and bioavailable in nature, and that is the only state that we should be worried about. So, as you know, we started discussing in the first lecture of thermodynamics that what mining impact does to arsenic concentrations. So, such examples are there everywhere, and we have to try to find out in what oxidation state it is, whether it is stable, whether it is going to precipitate out in any other form, or it is going to get absorbed to organic matter and then settle down. So, oxidation is extremely important, and redox reactions is continuously happening, very dynamic. Okay. So, therefore, we need a little bit of understanding of these kind of interactions. Okay. So, many elements in this periodic table can exist in more than one oxidation state, and of course, we know that from our chemistry classes that they are denoted by these Roman numerals, okay, given as with plus and negative symbols, and the oxidation state represents the electron content of an element which can be expressed at the excess. So, whatever electrons is available for exchange, either it is going to depleted in the number of electrons, it is going to accept, it is available to accept that much amount of electrons, or it has those electrons in excess than its stability form. So, it is going to give out to that electrons, right. So, it all depends on their stable state and how many extra electrons or deficient electrons it has. So, therefore, it can either give out those electrons and become more stable, or it will accept few more electrons to attain that stable electronic configuration. And again repeating, the solubility of some elements, that depends on the oxidation state. Okay. Now, so we are going to understand how the oxidation states are changing. So, we need to know how to write these reactions. Okay. So, how to write the reactions? Okay. For example, let us take this reaction where A and B with some electron exchange is forming C and D. Okay. So, this is the oxidized state which will get reduced after accepting these electrons, it will get reduced to this reduced products, okay, C plus D. So, we have this oxidized state which will accept again the electrons and it will become reduced. And often we try, if you are trying to write a reaction, we break down to write the oxidizing half and the reducing half initially when we are starting to learn how to write the reactions. Okay. It might help us to understand if we break down it into an oxidizing half and a reducing half. For example, let us take the simple iron's example. Okay. So, iron Fe2 plus, okay, it can easily give out one electron and get more oxidized to Fe3 plus. So, iron 2 plus gives out one electron to form Fe3 plus and the electron is left in the system. What will be the reducing half reaction? Here 4H plus oxygen and it will accept those electrons and it will form water. Why is this called oxidation and why is this called reduction half? See, in the oxidation half of the reaction, we are in the product, there is one electron, right. So, that is here this is getting oxidized, here iron is getting oxidized. So, this is the oxidation half of the reaction. Here H plus is getting reduced. In this half of the reaction, electrons are in the reactant side, it is getting absorbed, it is getting uptaken by the H plus ions, okay, and it is forming water. So, this is the reduction half of the reaction. Now, if we sum it, okay, if we are going to sum the reduction half and the oxidation half, so let us sum it. So, we find that 4 Fe2 plus 1 O2 will give 4 Fe3 plus 2 H2O. So, it is not that the electrons are going to be free in the water, it is to interact, okay, it will interact with the H plus ions there in the system freely, and it will interact with the oxygen that is available to form water, okay. So, this reaction we broke down into this two reactions, okay. So, this is how we can start writing equations, okay. Again, now, so we understand from this previous example that there is always a oxidation half and always a reducing half, and there will always be a oxidizing agent and always be a reducing agent, okay. So, there will be an oxidizing agent who will be available to uptake or accept that electron, and there will be a reducing agent who will give up that electron, right. So, in this case, okay, Fe3 plus is going to accept that electron. So, it is getting reduced. So, the oxidizing agent gets reduced, okay, and this iron is formed, Fe2 plus is formed, okay. In another equation, so 4H plus again oxygen is forming water, and if you are going to write the fundamental in, so you are just now trying to balance, okay. So, it is in the unbalanced state, it is Fe3 plus half of H2O producing Fe2 plus H plus 1/4 of O2. So, it is just understanding how you are going to write in terms of different kinds of oxidizing agents and reducing agents. So, there is a redox happening. So, a redox couple is formed, that means somebody who is going to accept the electron, somebody who is going to give up that electron, and often redox couples are seen in between metals, okay. In between metals means whichever have the highest tendency to give out an electron and another metal which will have another tendency to accept the electron, okay. For example, Fe2 plus, so Fe3 plus electron will become Fe2 plus, and copper 2 plus will accept an electron to form copper, okay. These are my reactions and these are not balanced, these are not in the balanced state. So, what we are seeing here, Fe2 plus, okay, it will give up one electron, it will change it, this will accept it. So, this is the reducing agent. So, reducing agent gives out the electron, okay. That electron will be accepted by my copper, right, and Fe2 plus will get oxidized to Fe3 plus, while my copper will accept and turn towards in the metallic state. So, it will become copper as metal, not in the ionized form, right. So, that will get reduced. So, this one oxidation agent gets reduced, and vice versa, you can have another reaction in this direction also, and in that case this will be the oxidizing agent, this will be the reducing agent. and this can happen multiple times in an environment depending on whether it is a oxic environment or it is moving towards more anoxic environment. So, continuously there is exchange happening until and unless it gets precipitated out as an insoluble which cannot further interact with the water. If it is there in the solution, it will go on interacting. Okay, it will go on interacting, getting released, again it is getting precipitated out. If that precipitation, if the precipitated product no longer interacts with the water, it will be there trapped. But if it can further dissolve, if it can again get remobilized in the system with the changing oxidation conditions, then again it will get back into the system, it will get again dissolved back. So, we have different kinds of environments where this is continuously happening. Okay. In a system, in an aquatic system, these can be present, okay. And this shows a kind of ladder. Okay. It starts with the most easiest one to the most difficult step, and at every level the energy drops. Okay. What is energy drop? During this exchange of electrons, some energy is utilized, okay, some energy is released, and that energy is utilized by the organisms, the microorganisms for their activities. Okay. For example, if it is O2 and H2O, so it is an oxic environment. Okay. Oxygen is there freely available for exchange. So, we are in a oxic condition. In that oxic condition, energy is the energy availability is very high. All the reactions that is there will happen, and the oxygen, the energy that is released will be very high. As we go down, we are moving towards down the ladder. So, there will be some post oxic conditions. That means, near the bottom of the aquatic system, by bottom I mean if it is a lake system, then at the bottom sediments, okay, or near wherever there is sedimentation happening, decaying of organic matter is happening on the banks, that place, okay, all these anoxic. So, it is it is so down that it is no longer exchanging a lot of oxygen with the water, it is not getting the fresh oxygen. So, here we are moving towards anoxic conditions. So, here there are different other reactions from which the organisms is supposed to take the energy. So, what they will do? They will break down the nitrates, they will release back the nitrogen. So, there will be action of the reactions of the nitrate breakdown, and nitrogen will form, and that reaction will give out the energy necessary for all the activities, all the life supporting activities that the organisms will be doing. Further little down you will have manganese oxides, okay. They will start dissolving and they will be released as manganese, okay. So, in oxic environment, manganese forms manganese oxide and it settles down, it is insoluble, it settles down, okay. So, in oxic conditions in aquatic environments, you will find the concentration of manganese is extremely low, okay. It will often be only in the form of manganese oxide. Only at those times where anoxic conditions arise, it will start again going back to the Mn2 plus state, and all this is catalyzed by bacterial activities. The microorganisms support these reactions, they are going to take up the energy that is released from these reactions. So, after manganese is iron, FeOH3, this is iron ferric hydroxide, okay. Ferric hydroxide will again dissolve back and it will release Fe2 plus in anoxic conditions, okay. So, oxygen is not available. Through these reactions, these organisms, they are going to take up their energy. After this also is exhausted, then we are moving towards sulfate reduction. So, sulfate reduction is going to release hydrogen sulfide gas. So, you see if we are looking into very deep sediments, buried sediments, there you will see formation of H2S gas, and in what conditions? Absolutely anoxic conditions. Okay. Sulfate breakdown will happen and hydrogen sulfide H2S gas is released. Okay. And again that reaction, whatever the energy is released, those bacteria depends on that energy for their activities. Just as respiration, we are our energy is all through respiration, we need oxygen. Okay. So, they are going to do that, they are going to use that reaction to accept, to gain that energy. Okay. And after that also is finished, after that level, after all sulfate reduction has happened, what is left now is carbon dioxide breakdown, and carbon dioxide breakdown to methane. So, only under extreme anoxic conditions is carbon dioxide getting broken down to form methane gas. Okay. And it is often seen in places which sees a lot of organic matter. So, there is so much of organic matter that your oxygen level is so low that you quickly surpass all these conditions and you start forming methane gas. So, these methanic conditions are often seen in places specifically in wetlands and any other inland lake conditions where the water is very stagnant, where the lakes are very shallow, okay, and there is extreme organic activity such that these conditions are surpassed very quickly and you go to the methane release reactions. Okay. Now, let us now see how to write in terms of electron activity. So, there is electron exchange, right. Now, as we defined something called pH when we were talking about acid bases reactions, our acidity or alkalinity depend on the H plus ion availability. So, pH gives us an indication of H plus ions in solution. Similarly, in the redox kind of reactions, to get an idea of the redox state, we are going to define something called the electron activity, that is Pe. And here it is equivalent to pH, it is minus log of activation of electron. Okay. So, it is minus log of the electron activity. Very similar, it is just like pH. Okay. So, pH was equal to minus log of activity of H plus ions, here it will be electron activity. And what does it indicate? It indicates the tendency of a solution to donate electron or accept a proton. If the P is low, there is a strong tendency for the solution to donate protons. If the Pe is low, the solution is reducing. If the Pe is high, there is a strong tendency for the solution to accept protons and the solution is oxidizing. So, high Pe is more oxidizing solution, low Pe means the solution is reducing in nature. Now, let us see how we write this in terms of a reaction. Okay. So, consider this half reaction. Okay. It is only half because it is only showing the acceptance of electrons and not the other half of the reaction. So, MnO2, okay, MnO2 is accepting electrons. So, 4H plus is there plus 2 electrons is getting accepted, Mn2 plus is forming, plus 2H2 is forming. Okay. Now, let us write this in terms of equilibrium constant. So, K is equal to activity of Mn2 plus, and of course, we do not write the activity of water because it is a pure liquid phase. So, we do not write liquid and gases, we are not going to write the activity term, right. So, we are going to write only this term, 1 term, 2 and 3. So, in the product side we are going to write Mn2 plus divided by activity of H plus ions and activity of the electron. Now, mind you, we are going to write the PE. So, we need the activity of the electron in our equal to side. So, I just reshuffle in terms of electron activity, and then it shows that activity of the electron is equal to A Mn2 plus and K into A H plus to the power 4. And since there was a whole square here, here we have a square root. Okay. Now, let us take log. So, you take minus log. If you take minus log, what will happen? Here it will come minus half log to the power A Mn2 plus into AH plus to the power 4 plus half into log K, right. Why this should have been minus, but now I am going to write it in plus term and I will move K to the numerator. So, this is my PE term. So, my PE is equal to minus half log of activity of Mn2 plus and activity of H plus ions. So, this means that at equilibrium is a function of Mn2 plus activity and the pH, and this K term of course depends on the temperature and pressure. So, PE basically depends on the activity of the free ion, the pH and the temperature and the pressure at which the reaction is occurring. So, this is how we are going to write the PE of a reaction. From any reaction that you are given, you should be able to write PE of the reaction. First, you are going to write the equilibrium constant. Okay. Since we are trying to find the PE, we are going to include the electrons and we are going to add that term, and then we are going to solve in terms of electron activity, we are going to solve in that term. Okay. So, whatever is there in the ionic state, we will have that. H plus ions is there, then we know we will have a pH term, and of course, K we are going to have. Now, you see, we know what is this term log K. Okay. We know this term called log K. Okay. And we can calculate that. Where we can calculate that? We can calculate that from the delta G term. Okay. We can calculate that from the delta G0 R. What is R for? It is for the entire reaction. How do we calculate minus del G R? We are going to calculate it from the formation reactions. We are going to calculate it from the formation reaction. So, delta G0 of Mn2 plus, delta G0 F of H2O and delta G0 F of MnO2, and those values are always there. Okay. These values, the formation values are always there. Okay. So, we just plug in those values. Okay. You consider RT as temperature to be normal 25 degree condition, and you find what is the PE. Okay. So, log K value comes out to be 43.65. Therefore, our PE, if I just plug in here half of that 43.65, So, Pe now becomes minus half log of Am2 plus and Ah plus to the power 4 plus half of this value. So, that is 21.83. So, now you just have to know what is the pH of the solution, and you need to know how much is the manganese 2 plus concentration. If you know this, these two values, you can easily find out what is the PE of the solution. Now, let us define another term called EH, okay, and these are absolutely the same thing, it is just how we measure it. Okay. PE is measured from this process. Okay. So, from the reaction we need to find out the log K, we need to calculate it. Now, you can also measure it, okay, and often it is measured with respect to a SHE. SHE is a standard hydrogen electrode. So, another method of noting or measuring the redox potential is EH. So, one is PE, another is EH, and we are going to measure that. We are actually physically measuring that using a standard hydrogen electrode. It is basically measuring the same thing. Okay. One is using a particular electrode, that is EH. So, when we are measuring through the electrode, we call it the EH, and if we are just trying to derive it from the reactions, we are going to say it in terms of PE, and we can interconvert them. So, PE is equal to, this is called a constant, which is the Faraday constant, divided by 2.303 RT into AH. So, this is entirely a constant term at a particular temperature. So, essentially at this room temperature, at it is 25 degree standard condition, PE is 16.9 EH. So, you just multiply EH value into 16.9 and you get the PE value, or vice versa. If you know the PE value, you multiply 0.059 and you get the EH value. So, calculable, right. Now, how does this reaction relate to the driving force, that is the free energy, the del G? The delta Gr, that is that free energy of the reaction, is equal to minus NFE, where N is the number of electrons it is getting exchanged, F is again the Faraday constant, and E is the electropotential measured of that reaction. Okay. So, minus NFE. Here this is important, that is the number of electrons exchanged in that reaction. Faraday constant is a constant term and electropotential you are going to measure. So, when we are in an aquatic system, okay, who is going to get oxidized, who is going to get reduced, depends on all these EH values and PE values. Okay, depends on its electropotential and the PE of the system. Those which are on the top part of this list, they are very strong reducing agents. That means they have very high tendency to donate electron. So, this alkali element lithium, very stable it will become if it gives out one electron. So, it will quickly give out that electron and become lithium. So, it will become lithium plus. Okay. So, it will go on its tendency, it is more towards getting into the ionic form. So, lithium plus. So, if you want it to convert it to lithium, it will be very difficult. Okay, its PE state has to be very low, electropotential is very high. Okay, as compared to this copper 2 plus, copper 2 plus will accept electrons and become copper metal, and its electropotential is also low and its PE conditions you see is positive. So, these are strong reducing agents, these are strong reducing agents, that means they are just going to donate electron, and these are strong oxidizing agents, that means they are going to accept the electron, oxidize the other reactant, and they themselves are going to get reduced. So, in a system if there are multiple elements coexisting, this is often going to oxidize this one. Okay. This will have the tendency to oxidize the one which is in the higher in the list. Okay. So, when we are observing or doing calculations for a particular system, we always need to see what kind of redox couples can be formed, okay, how they are going to exchange electrons, how given the electropotential of the system, how the PE of the system, how they can exchange electrons, in what fundamentally if you have somebody here, is it going to oxidize somebody who is here. So, those kind of transitions we need to be cognizant about in an aquatic system, because in an aquatic system all of these elements are going to be present. Okay. So, the one which is the highest strongest oxidizing agent, they will remain in that, they will quickly absorb the electrons and they will remain in their most metallic form. As compared to these elements, the reducing agents, they are going to give up the electrons and they are going to be in their ionic form. Okay. So, with this I am going to stop this lecture today, and I am going to continue this lecture in the next redox reactions in the next lecture.